Hello, this is Sashank Shrikant and my other teammates are Gulshan Kumar and Nikhil Bansal. Today, we would be discussing about edge-chasing deadlock detection algorithms and how they work under various message delivery guarantees. We would be also be discussing the asymptotic analysis. So, the main motivation for distributed systems is resource sharing. A process can only obtain the resource if it is released by the previous resource using it. There are several complexities associated with resource sharing, such as order of resources for request, acquisition, and release is unknown. Similarly, the order of processes is also unknown. Thus, these complexities make distributed systems prone to deadlock. There are several different models of deadlock, such as single resource model, AND model, OR model, and so on. However, in this project, we simply deal with the AND model. There are several types of distributed deadlock detection algorithms, and they are path pushing, edge chasing, diffusion computation, and global state detection. However, in this project, we will be studying particularly the edge chasing deadlock detection algorithms under various message delivery guarantees and also perform asymptotic analysis on the number of messages required to detect the deadlocks and the time taken for the same. In edge chasing algorithms, presence of cycle is usually determined by propagating special messages called probes along the edges of the graphs. They are different than the request and reply messages, and the formation of cycle is detected by seeing if the initiator receives the matching probe sent by it previously. These probes are of fixed sizes, which are normally short, and hence the memory used is less. In the Chandy-Mishra-Haas model for AND model, we have a probe message that consists of three terms I, J, K. I is the initiator process I, and the J denotes the home site of process Pj, and K denotes home site of process Pk. Pj and Pk belong to two different sites. A probe message travels along the edges of the global wait for graph, and deadlock is detected when the probe message returns to the process that initiated it. There is only one main data structure used in this algorithm called the dependent I array, which is true only if Pi knows that Pj is dependent on it. We won't be discussing the algorithm in detail as the same has been done in class. The asymptotic complexity of this algorithm is m into n minus 1 by 2 for the number of messages, where m is the processes and n is the number of sites. Another algorithm for edge chasing is the Mitchell and Merritt's algorithm. Each node in the wait for graph has two local variables, which are the private label and the public label. Initially, they are the same, and then these values get updated by four different types of transitions, which are block, activate, transmit, and detect. So I would again not be discussing in detail this algorithm as the same has been done in class. However, we should note that the worst case complexity of the algorithm is n into n minus 1 by 2, where n is the number of processes in the cycle. This example here shows the detection of deadlock for the following three processes, and we can see that initially the private public labels are equal, and we find that P1 is waiting for P3, P3 is waiting for P5, and P5 is waiting for P1, which is a deadlock. We further see that the transmit and block messages are being sent, and finally we do deadlock detection in the last portion of the figure at the bottom. To simulate the Chandy-Mishra-Haas algo for the AND model to detect deadlocks, we utilize the modified dining philosopher problem. In this, the philosophers are sitting and they have two states, which is thinking or eating. This is a common problem and has been studied earlier in operating systems. So, aside from the two folks in the common problem, we modify it such that philosophers must also have soup and bread before he or she can eat. There are three options for the same, and they are mentioned in the bullet points below. In this problem, each philosopher, that is philosopher I, can be treated as a site Si in which the activity of eating is the process Pi. Also, I would again repeat that the order in which things can be done are mentioned in the bullet points above. This figure shows an example of the modified dining philosopher problem with soup and bread as well, apart from the fork. So, for testing our algorithm, we have a simple wait for graph for five philosophers as shown below and shown here, and we can see that there is a cycle present in this and hence a deadlock. How did we do deadlock detection for this case? We find that we, as the philosopher waits for the resource, he or she will create and send probe to the philosopher holding the resource. If receiving philosopher is also waiting for the resource, then he or she will further send probe to the philosopher holding that resource. We keep on doing 1 and 2 until the philosopher that initiated the probe becomes the philosopher receiving the probe. So let's see the results of our experiments. We experiment the Chandy-Mishra-Haas algorithm for this dining philosopher problem with various number of nodes. We vary the number of nodes from 5 to numbers as large as 10, 50 and 100. We see that the number of messages for the detecting a deadlock increases linearly with respect to the number of nodes present in a cycle. The same can be said about the time taken, that is, the time taken also increases linearly in this case. We also find that Mitchell algorithm takes more time than the Chandy-Mishra-Haas algorithm for the same experiment, that is 5 nodes. This is an example of the output of our code where we display the sending and receiving of the probe from one node to the other until a deadlock is detected. This example shows the test for 10 philosophers, and we find that a deadlock is detected with 9 probe messages. That is, the cycle length was 9. We also test our algorithm for non-FIFO message ordering by inserting random time.sleep before each probe message. Hence, the messages may not reach in the same order as in which they were sent. However, our implementation could not detect deadlocks correctly if the message delivery scheme was non-FIFO. We believe this is because the Chandy-Mishra-Hask algorithm works well only on FIFO order as mentioned in the original paper. The same holds true for the Mitchell algorithm as well, as it does not support non-FIFO ordering of message communication. As Mitchell algorithm does not consider synchronization mechanism, it may detect phantom ad block sometime due to asynchronous message passing. In conclusion, the Chandy-Mishra probe messages are a fixed size which are short and there is no message overhead. Hence, the time complexity scales linearly with the number of sites and is m into n minus 1 by 2 if there are m messages in each site. In Mitchell and Merritt's, only one deadlock process detects deadlock. This is a major advantage as deciding which process should initiate deadlock resolution is not needed. The message overhead is low as labels are of short size. In another conclusion, we state that we experimented with two algorithms, Mitchell-Merritt and Chandy-Mishra-Haas, and we find that the time complexity scales linearly in the case of Chandy-Mishra-Haas algorithm as the number of nodes in cycle are increased. We also tried two different message delivery guarantee scheme, that is FIFO and non-FIFO, and have reported the results for the same. Thank you.